Equilibria lies at the heart of many areas of chemistry, and at A level, this Year 12 equilibria topic is really split into two parts. The first part mirrors equilibria, how you explored it at GCSE, so it gives a sort of a qualitative sense of equilibria, and it's centered principally around Le Chatelier's principle, which you did at GCSE. And then the second part is essentially looking at it in a more qualitative sense, so a mathematical sense, where we actually see values and actually get a sense of the position of equilibria and so on. But anyway, this first video is focusing on the qualitative aspect, and that's where we're going to start. And so we just need to understand a few key ideas and terms before we sort of delve deeply into the topic. So the first thing to appreciate is that many chemical reactions are reversible, and at GCSE we showed that by using this symbol. So instead of having an arrow just in one direction, we had these two half-headed arrows, one pointing in one direction, one pointing in the other. And that told us that the reaction could proceed in both ways. And the particular example that many specifications look at GCSE is the one where we have hydrated copper sulfate on one side and anhydrous copper sulfate and water on the other. Now, we knew that a chemical reaction was taking place because of one of those classic observations, and that's a colour change. So hydrated copper sulfate is blue and anhydrous copper sulfate is white. The other piece of evidence that we had that a chemical reaction had taken place in either direction, as well as a colour change, was there was clearly an energy transfer. To make this reaction take place, we had to heat the hydrated copper sulfate. So the forward reaction was an endothermic reaction. Now, one of the great things about chemistry is that if we know the energy change in the forward direction, then the energy change in the reverse direction will be the opposite. But how we could actually observe that was if we'd let our anhydrous copper sulfate cool down, and then we added some water, you would have very clearly seen that was an exothermic process, because the resulting solution got incredibly hot just simply from adding water to a sort of room temperature anhydrous copper sulfate. So the reverse reaction was exothermic. Just as a slight aside, if we look at this reaction equation, we can now understand that it's actually an example of a thermal decomposition reaction. So thermal, basically because we're having to constantly heat it for the reaction to take place, and decomposition because we have a single reactant breaking down into more than one simpler substance. Anyway, this was our classic example at GCSE of a reversible reaction. Now at A level and beyond, this symbol, this double half-headed arrow, is going to tell us that the reaction in question is an equilibria reaction. So now we need to understand what we mean by equilibria or equilibrium. Now the word equilibrium is used to denote balance. So one way we can think of balance is two people balanced on a seesaw, and we would describe that as an example of static equilibrium. Equilibrium because they are balanced, but static because there isn't actually anything changing either. If we think of an example of somebody running on a treadmill, we still have equilibrium because we have the position of that person is essentially balanced. Their position is fixed, but it is a combination of the person running forwards and the treadmill moving backwards, and as a result of that, we would refer to that as being dynamic equilibrium. So even though the position of the person is balanced, let's say right in the middle of the treadmill, there are two things constantly changing. The person is trying to run forwards, the treadmill is moving backwards. So we would describe this as an example of dynamic equilibrium. In chemistry, equilibrium is dynamic. So what that means is that we have the forwards and backwards reactions taking place at the same time, and the rates of these forwards and backwards reactions are such that the amount of each substance on both sides of the equation stays the same. They are in equilibrium, but equally they're constantly being produced. There is a forwards reaction, there is a backwards reaction. They are constantly happening. They are happening at the same time. They just happen to be at the same rate. So how things appear is that nothing is changing. Now, dynamic equilibrium can only be achieved in a closed system. And what we mean by a closed system is one in which there is no loss or gain of materials to or from the surroundings. Now, one sort of useful example of this, I guess, is if you've ever bought a fizzy drink, and you may have bought it from the supermarket or the newsagent or wherever, you've taken it home, you've put it in the fridge, and maybe you haven't drunk it for 3, 4, 5 days, or even perhaps longer. And when you open that bottle, you know it's as fizzy then at the time you open it as when you bought it 4 or 5 days earlier. If you leave that cap off, you know that fizz is essentially going to disappear over a relatively short space of time. So if you left it another day or two and you'd left the cap off, you know that when you come back to it, it's not going to be fizzy anymore. Now, with the cap on at the beginning, that was our closed system, and in effect, actually, there's an equilibria set up between the carbon dioxide in the sort of the actual drink itself and the carbon dioxide in that little gap between the lid and the liquid. But the moment that that's a closed system, but the moment you open your bottle and you leave the lid off, you now have an open system. So equilibria can only or dynamic equilibria can only be achieved in a closed system, and a closed system is our sealed bottle of fizzy drink, and our open system is one where we've left the lid off and which eventually goes flat. Now, crucially, it's very important when we're thinking about dynamic equilibrium that we definitely don't see it like balancing a seesaw, or at least what's crucial is that there doesn't need to be equal concentrations of reactants and products in the equilibrium mixture. So we've got an equal rate, we've got an equal forward and backwards reactions, but what we don't necessarily have is equal amounts on both sides. So this is why we talk about position of equilibrium. So imagine this is at the top, we've got is a diagram of a very long treadmill, basically, okay? And if we think about the far left, we could say, well, that's when it's 100% reactants. And if we think of the far right, we can think of it as 100% products. And if we had a reaction that went to completion, it would go all the way from the reactants all the way to the products, and we would just be left with products. Now, in equilibrium, we're saying that there is a sort of a balance between the reactants and products, but the balance is about the rates of the reaction. It's not about the amounts of reactants and products. And so we talk often about the position of equilibrium. So this person here is on the treadmill, and their point at which they're no longer moving, or there's no change, is where we've labelled this position of equilibrium. And if we think about it being 100% reactants and 100% products on those two sides, those two extremes, we're saying that the person is, or the reaction is balanced at equilibrium, much closer to the reactant side. So what we can deduce from this is at equilibrium there is more reactant than product. Now, if we sort of try and sort of show that on a graph, one way we can do that is to do a concentration against time graph, and to show how the concentration of both the reactants and the products changes during, well, once the reaction starts and then until it reaches equilibrium. So let me just show you that. So at the beginning, the reactants are at their maximum concentration, and they increase most dramatically at the beginning because that's when the rate's fastest. And then at some point, and you have to excuse that they no longer change, okay? If we think about the products, there are no products at the beginning of this reaction. So they are increasing greatest at the beginning, and then they also get to a point where they no longer change. So to begin with, there is just reactants. As the reactants produce the products, we now have the possibility of the backwards reaction. The products can form the reactants. So we have a forward reaction of reactants to products, and we have a backwards reaction of products to reactants. And this reaction reaches equilibrium when the two concentrations are no longer changing. So it looks now as though nothing is happening, but actually what we've got constantly happening is reactants forming products and products forming reactants, but they're doing so at the same rate. So the concentrations of reactants and the concentrations of products remain unchanged. Okay, so what if our position of equilibrium lies somewhere in the middle, somewhat, basically halfway between the reactants and products? How would our concentration time graph look in that respect? So the basic shape of the curves will be the same. What differs is where they finish. You have to excuse this, that's supposed to be a straight line. So that's our reactants. So obviously we just start with reactants. So again, our products are 0 at the beginning of this reaction. And what we notice is that there should be sort of like a symmetry to them, and they both finish at roughly the same concentration. Of course, I'm simplifying a little bit by assuming the proportions of reactants and products are exactly the same, but you get the basic idea, I hope. And so we again have equilibrium being reached because the concentrations are no longer changing. Finally, our position of equilibrium could lie to the right. So at this equilibrium, there's more product than reactant. So if we were to consider how the concentration of the reactants changes and how the products changes and how they sort of relate to each other, then again, reactants is maximum at the beginning, and what we would find is that we would get a shape something like this in terms of their concentration. And then if we looked at the products, again, it's going to be 0 at the beginning for this example. We might get something like that. And again, we still can show once the concentrations are no longer changing, we know that's when equilibrium has been reached, when the concentrations, basically concentration over time is a constant, it's a 0 gradient. Just before we move on, it is just worth comparing how the rate of the forward and backward reactions compare from the moment, say, the reaction starts to when it reaches dynamic equilibrium. So this time, just be careful. What I've got on my y-axis is the rate. So that's going to be referring to the rate of the I'm going to be drawing the forwards reaction first and then the backwards reaction second. So the forwards reaction was reactants to products as far as we were concerned in our example. So the rate is greatest at the beginning, and then the rate decreases because the concentration of the reactants decreases. So there are fewer, or the frequency of successful collisions decreases, but then the concentration stays the same, so the rate stays constant. If we think about the backwards reaction, there are no reactants, there are no products to form the reactants at the beginning of the reaction because they haven't been formed. Then as the concentration of the products increases, the rate of the backwards reaction increases until eventually we get a constant rate of reaction. So what this graph is showing us is that once equilibrium is reached, which is when the two lines are horizontal, and that's a constant rate, that means the forwards and the backward rates of reaction, not only are they constant, but they are happening at the same rate. Okay, so they're happening at the same rate. Okay, so I've got a title here that says the five key features of dynamic equilibria. Actually, I want to just tweak this slightly. Really, in terms of anything to do with anything that they may or could ask an exam, there are really 4 that they're interested in, and I'll tell you. So 4 of these 5. So the first one I've included because I feel it's just important to repeat is that when you're looking at the large scale, when you're looking macroscopically just means, say, you're observing your bottle of fizzy drink, and then everything is constant, nothing's changing. So it looks, it's in equilibrium, but it looks like that's it. It actually appears to be static. But really, we now know that it's dynamic, and it's dynamic when we look at the sort of the molecular or particle level. So anyway, the four key features, so really 2, 3, 4, and 5 here, or that equilibrium can be attained from either direction. So we've focused so far on this idea of reactants and products. So we read a reaction equation from left to right, but we equally could have just started with the products in our example, in the sort of the previous sort of position of equilibrium examples. We could have started with the products. That would have made the reactants. I know that sounds slightly odd, but if we're just reading it from left to right, and we would have reached the same position of equilibrium. You can only achieve equilibrium in a closed system, so that's incredibly important. And then, of course, at equilibrium, we've got the rate of the forward process or rate of the forward reaction is the same as the rate of the reverse process or reverse reaction. And then something else to really emphasize and to bear in mind is that the position of equilibrium can lie anywhere between 100% reactants and 100% products. So it isn't automatically in the middle. It could be that at equilibrium we've got far more reactant than product, or we've got far more product than reactant. So those are sort of the key features of dynamic equilibria. So this brings us to Le Chatelier's principle, which I'm sure you did at GCSE, albeit briefly. So there are different ways of actually phrasing Le Chatelier's principle, and actually that's not really important, and you're never going to be asked, as far as I'm aware, to actually give Le Chatelier's principle. What you're always going to have to do is apply it. But if we look at these two sort of versions here, so the first one is a more traditional version of the principle. So if a system at equilibrium is subjected to a small change, the equilibrium tends to shift so as to minimize the effect of the change. So in other words, trying to summarize that even further to make it clearer, the position of equilibrium shifts to try to cancel out any changes you introduce. So we're going to think about what those changes you could introduce are, and then we're going to think about how we can then understand or how we can talk about the position of equilibrium shifting, moving. We're going to be talking about it shifting either to the left or to the right. So if we think about our person on the treadmill again, their position could be shifting to the left towards the reactants, or it could be shifting towards to the right towards the products. So for the moment, we're just going to consider the sorts of changes we could make, and then if the idea of the Le Chatelier's principle says that it seeks to oppose it or seeks to cancel it, then we think, what would that fundamentally mean? Not how could it do it, but what would that fundamentally mean? So if the change we made was to make it hotter, then what the equilibrium is going to, or the action by equilibrium is going to try and do is make it cooler or cool it back down. Okay, so we've got to think, when we're talking about the position, how could changing the position cool it back down? That's how we're going to think about this. If the change we made was to make it cooler, then the action by equilibrium is going to be to heat it back up. Again, we're going to think, how could it achieve that? If we added more chemicals, so it could be one of the reactants, could be one of the products, whatever it is, it doesn't matter. But if we add more chemical, what could the action by equilibrium be? How could it restore balance, as it were? Then it's going to use it up. Okay, whatever we add, it's going to use it up to get rid of it. So it's trying to cancel our change, right? That's what it's trying to do. It's going to try to cancel our change. What if we remove some chemical? Again, doesn't matter whether it's reactants or products. How is it going to cancel that change? It's going to try and make more of it. If we increase the pressure, then if it seeks to cancel it, it wants to reduce the pressure. And if we decrease the pressure, then the action by equilibrium is trying to cancel it, so it's going to try to increase the pressure. So we're going to consider how shifting the equilibrium can achieve or can cancel any of the changes that we're sort of suggesting on the left-hand side here. So I've got an example reaction. It's just a very sort of simple, basic one. A plus B are the reactants, or A and B are the reactants, C and D are the products. It's a equilibria reaction. Delta H, if we remember from energetics, means the change in enthalpy, or the change in energy, essentially. We're saying it says it's positive, so whenever you're given this sort of information, again, thinking back to the energetics topic, this is always referring to the forward reaction, right, from the left to right reaction. So a delta H that's positive means that that is endothermic. So they are telling us that the forward reaction is endothermic. I always think it's a good idea to write these things over the reaction arrows. And then, of course, if the forward reaction is endothermic, that means the backwards reaction is exothermic. And that's one of the reasons why I think it's good to write these things, because it just reduces a burden on our brain, if you like, in terms of our having to think. So if we increase the temperature, then we have to think, what are we fundamentally doing? One way to think of this is that if you increase the temperature, then you're essentially increasing the energy in the system. Now, we said that the action by equilibrium is an attempt to cancel this. So if we've increased the energy, then it's going to try and cancel this by decreasing the energy. Now, how can it decrease the energy? The only way it can do that is to take that energy in. And the way we achieve that is through the endothermic reaction. So we're going to shift in the endothermic direction, all right, because that is going to take in energy from the surroundings. That's going to take in, hopefully, the excess energy that we've put in, or the extra energy that we've put in. So in our example here, that would mean the endothermic direction is left to right. That would mean if we're shifting in the endothermic direction, because we're trying to remove the extra energy that's been added, so the position of equilibrium will shift to the right in this particular example. But the crucial thing is, increase the temperature, you shift in the endothermic direction. Okay, if we decrease the temperature of the system, then in effect we're decreasing the energy in the system. And so the position of equilibrium will shift to try to cancel this decrease in energy. So it needs to regenerate the energy, or it needs to add more energy into the system. So it's going to do that by favouring the exothermic direction, which releases energy. And so it's going to shift in the exothermic direction. So in our example equation here, our exothermic direction is from right to left. So our position of equilibrium would shift left in our example here. But fundamentally, if you decrease the temperature, you favour the exothermic reaction, or you favour the exothermic direction. So the reaction will shift in the exothermic direction. So now we look at concentration. So if you increase the concentration of one of the substances, the position of equilibrium will shift in an attempt to cancel this increase. So that means it will shift to the other side. So for example, in our equation above, if we say increase the concentration of A, then the action of the equilibrium is an attempt to cancel this. So we need to reduce the amount of A. So what will happen is the equilibrium will shift to the other side. It will shift to the right-hand side. What in effect will happen is we will produce more of C and D. Similarly, if you decrease the concentration of one of the substances, the position of equilibrium is going to shift in an attempt to cancel this decrease. So if we say decrease the concentration of A, the position of equilibrium will shift so as to increase the concentration of A to sort of cancel the change that we made. And to do that, it must shift to the left, which will mean that we will have less of C and D than we had at the beginning. So if we decrease the concentration of a substance, we shift, the position of equilibrium will shift to the same side. So if we decrease the concentration of A in our example, it would shift to the left. Finally, we come to pressure. So if we increase the pressure, the system seeks to decrease the pressure. And pressure comes from, basically, it's force divided by area. So pressure is force divided by area. And so what we're looking at or considering here are the particles, whatever they are, molecules, striking the sides of the container. Remember, this is a closed system. So if we increase the pressure, we've got to have fewer, to decrease it back to cancel that change, we've got to have fewer collisions with the side of the container. So what will happen is the position of equilibrium will shift to the side with the fewest molecules, because that counteracts the change, because it is a way of reducing the pressure. Similarly, if we decrease the pressure, then to cancel that, we need to have more collisions, more particles colliding with the walls of the container. So we will shift to the side with the most molecules. Now, it doesn't follow that there is always a side of the equation with greater or fewer molecules. If you look at our reaction example, A plus B goes to C plus D, if we counted the number of moles or the stoichiometric moles on the left, it's 2, and if on the right it's 2. So actually changing the pressure would have no effect on the position of equilibrium for our example reaction, because there isn't a side with more or fewer molecules. So just bear that in mind, please. So let's just look at one or two examples. So here's an equilibrium reaction. If the position of equilibrium is far to the left, it's going to look yellow. The mixture, if it's far to the right, it's going to look blood red, and it's asking us how we can make the solution a darker red. So what that's really asking us is how can we shift this position of equilibrium to the right. Now, pressure isn't relevant because we've got everything in the aqueous state. And as far as changing the temperature is concerned, we don't know which is the exothermic or endothermic direction in this reaction. So really what this question is asking us is how can we change the concentration, or what concentration can we change to make the solution darker red. So we need to shift the position to the right. So the simplest thing to do is to increase the concentration of either the Fe3 plus or the SCN minus. If we increase the concentration of either of those, then the position of equilibrium will shift to the right, because it will seek to cancel that increase, to cancel that change. And to do that, it needs to use that increase up, or some of that increase up, which is then what means that it shifts to the right. So we can make the solution a darker red by increasing the concentration of either the Fe3 plus ions or the SCN minus ions. Okay, so we're making ammonia here from nitrogen and hydrogen. Okay, so we're told that the forward reaction is exothermic, so we're going to write that, which means that the reverse reaction must be endothermic. And we've got everything is in the gaseous state, so another thing that we can consider is the number of molecules on both sides, because we can think about how pressure can affect the position of equilibrium. So we've got 4 moles on the left, and we've got 2 moles on the right. So we're trying to, or we're being asked about how we can increase the yield of ammonia. So that basically means how can we increase the amount of ammonia that we make. So yield just means how much you're making. That means we want to shift the position of equilibrium to the right. So let's consider the energy, or changing the temperature first. So the forward reaction is exothermic, so we want to favour that reaction. We want to shift it to the right. Now, if you remember from our table on the previous page, if we want to increase the direction or shift the equilibrium in the exothermic direction, then what we need to do is decrease the temperature. If we decrease the temperature, we're in effect reducing the amount of energy in the system. The action by the equilibrium seeks to cancel that, so it wants to restore that energy in the system. So the way it does that is to favour the exothermic reaction, which releases energy. And so that's why we're, if we, in this particular one, we decrease the temperature, it shifts in the exothermic direction, which is to the right, and we would produce more ammonia. The other thing we can consider is pressure. So we want to shift it to the right. We've got fewer moles on the right compared with the left. So the way that we would shift it to the right is to increase the pressure. If we increase the pressure, the system seeks to cancel that increase, so it wants to reduce the pressure. Pressure is a measure of the force divided by area. So in part the collisions against the side of the container. One of the things that we can change is the number of particles that are colliding with the container. If we shift to the right, there will be fewer particles hitting the sides of the container. So that is the way that we can act against the increase in pressure. Now, we looked at catalysts when we did kinetics. So catalysts speed up the rate of a reaction without themselves being changed. Now, when it comes to equilibria, catalysts do not change the position of equilibrium. And that's because the rates of both the forward and backwards reactions are sped up by the catalysts. So while the position isn't changed, the time it takes to reach equilibrium is decreased, and that is one of the reasons why, or that is the reason why, you will still see catalysts feature in equilibrium reactions. It's not that they are changing the position of equilibrium, but they are speeding up the forward and backward rates, so they are allowing you to reach equilibrium in a faster time or faster period of time. So the final part of this aspect of equilibria is sort of its application in industry. So we've got the production of ammonia equation again. This is called the Haber process. So it's a very famous, very influential, very important reaction, believe it or not. And what we've got here is we have sort of a graph, and along the x-axis we've got pressure, and along the y-axis we've got yield. And the other thing we've got is we've got a number of lines which represent how the yield is changing, or how the yield would be, at different temperatures. So on the surface, if we wanted to maximize our yield of ammonia, then if we are looking at these lines, then we would be looking at a temperature of 350 degrees Celsius and a pressure of 400 atmospheres. And yet that isn't what's actually employed, or those conditions aren't what are actually employed in industry. In industry, they use a temperature of 450 degrees Celsius, and they use a pressure of 200 atmospheres. So if we were to plot, if we would see where that is on these graphs, we would be looking at here. So why are they choosing the conditions that they are, the actual conditions, as opposed to what we might think of as ideal conditions? So this is because there are other factors besides the actual yield. So what we can't ignore is kinetics. What we can't ignore is the rate of reaction, and that is also affected by temperature. So just as the position of equilibrium is affected by temperature, so is the rate of reaction. And there's an antagonism here, because the ideal temperatures are for making or increasing our yield of ammonia are lower temperatures. So a lower temperature increases the yield of ammonia, but a lower temperature would slow, or decrease, I should say, the rate of reaction. So there's an antagonism there. There's a sort of a tension between the rate of reaction and the position of equilibrium. When it comes to pressure, a high pressure would give us the greatest yield, but the only problem is that pressure is very expensive. You've got the safety equipment, or the equipment itself is very expensive if you're going to contain those high pressures, plus you need a great deal of energy. So what we're looking at here is we're looking at compromises. So one of the things that's part of the A-level spec are compromise conditions. So on the surface, for this particular reaction, if we want to increase the yield of ammonia, we should have a low temperature and a very, very high pressure. But the reality is that we compromise on that, and we compromise possibly because of rate of reaction, certainly in this instance, and possibly because of costs. So that's the sort of final aspect of this sort of qualitative part of the equilibria course. We'll just write those, we'll just make a note of those particular conditions for this Haber process. It's not that you necessarily need to remember those actual temperatures and those actual pressures. But what I think you do need to understand is the reasons behind why there might be a compromise. So to confirm, we have a temperature of 450 degrees Celsius. So the lower the temperature, the greater the yield of ammonia, because the forward reaction is exothermic. However, the higher the temperature, the faster the rate of reaction. So this temperature of 450 degrees Celsius is a compromise between yield and rate. So we use a pressure of 200 atmospheres. If we look at the reaction equation at the top, we've got 4 moles on the left, 2 moles on the right. So a high pressure gives a greater yield of the ammonia, which is on the right, because there are fewer moles there. However, high pressure is very expensive. We need to pay for strong pipes. There's a lot of energy needed. So we use a compromise pressure of 200 atmospheres, and this is a compromise between yield and cost. One final thing to say here about the Haber process is that they would use a catalyst also. Now that's not going to affect the yield, but it is going to affect the rate of the forward and backwards reactions, and they use an iron catalyst here. So to sort of finish this topic, you just have to be aware that there are such things as compromise conditions. So there are many industrial processes that we rely heavily on. So the Haber process is the one that's typically picked out. And when we're talking about industrial processes, there isn't just the position of equilibria, which is therefore determining the yield of whatever it is that we want to make. That's important. There are other factors such as cost and the rate of reaction. So just to be aware that there are quite often things that we can consider to be compromise conditions. So they aren't automatically the conditions that would absolutely maximize the yield. It depends on which direction is the exothermic endothermic reaction. It depends on the cost of energy. It depends on the cost of the equipment that would be needed. So just bear that in mind. But otherwise, that basically concludes the qualitative part of this topic. A lot of it had featured at GCSE, so a lot of it in a sense was a recap and a slight extension of what you've done at GCSE. The next part of equilibria is totally brand new, and that's when we look at equilibria from a quantitative perspective. Anyway, if you have any queries, just let me know.